All right. Can you see my screen okay?
Yeah, good.
Okay. All right. So we'll go through this, and then if you have any questions along the way, your face, your video feed isn't being recorded, so I would other students would only hear your voice. Okay. All right. So if you remember chapter 8, the kind of big idea of this chapter is we're going to learn a new method for solving differential equations. This is a much more powerful method. It's much more robust. It can handle more difficult differential equations. It's basically the idea of using series to find solutions. And there's a couple different methods we're going to look at. One of them is the power series method, which will be our focus in 8.3 and 8.4. And the other one is the method of Frobenius, which handles some more crazier differential equations. I'll talk about what I mean by crazier in a minute. So most of the discussion today will be on just kind of a review of power series, but it's been a long time, and maybe in Calc 2 some students didn't get a firm grasp of what they are. So we'll do that. That's most of the section, but then also we're going to discuss a topic called analyticity, which you're going to want to understand what it is. It's basic, but it's just a weird way of it's a weird name. So but it'll help later on. So hopefully that is that big enough for you to read. I know you don't need to read through this with me. I'm going to pull out the most important parts and highlight them.
Yeah, that's
Okay.
good.
Yeah, so like I said, we're gonna review power series from Calc 2. We're also going to talk about analyticity. And this rule we're going to um, the reason we're doing this is to prepare us for the power series method, also for the method of Frobenius. Okay, so by the way, this will handle things that we couldn't really handle very well in the previous chapters. For example, solving linear equations with variable coefficients. We could do some of them, the Cauchy-Euler ones, and there may be some others that we worked on, but I think that was pretty much it. So what if they're not Cauchy-Euler, or what if you're working with nonlinear equations? First order we're okay, but once it just starts getting really complicated. So this will allow us to get at those, including all the ones we already know how to do using other methods. So we're going to develop the theory from the ground up. And one of the things you do need to know is that you do kind of have to have a foundation of knowledge of series of constants. So this is where there's no variable involved. So this is the first part in your Calc 2, where you had a bunch of constants and you're adding them together. So there's no x basically, but there's a bunch of series tests. So you want to review those, like the divergence tests, comparison tests, limit comparison test, ratio test, integral test, all that stuff, and it'll be peppered throughout the rest of the sections that we cover in the class. So you'll kind of want to have a understanding of what we're talking about when we get to those, because I'll just say, oh, by the divergence test, this happens. Okay. So the first thing to note is to discuss, well, these are the kind of the topics we're going to go through. So we're going to talk about what it means for a function to be an elementary function. Have you heard of this term before?
Yeah.
Oh, okay. And then we'll discuss what a power series is by definition. We'll talk about finding the interval of convergence for a power series. Whenever you find a power series, it's a good idea to know the interval of convergence, because that tells you when you can use it. Really, you can create a power series, but maybe it's useless. You need the interval to know when you can use it. And then we'll talk about interpreting power series as functions. You definitely want to do that. And then there's a whole algebra of power series where we can add and subtract, multiply and divide them. Then there's the calculus where we can take derivatives and integrals of power series. And then this part's pretty important, which I found when I used to teach Calc 2, it's kind of the point where it either the class kind of split in two. There's some students that really got it and some didn't, and it's because of the indices and shifting indices and changing names and stuff. So that turns out to be really important for the next few sections. And then we'll discuss analyticity, and then we'll finish off by discussing kind of going back and recapping on what Taylor series were from the previous section. And then there's a little table here, and it worked out a few of these from your homework. Okay, so what is an elementary function? Well, an elementary function is one that can be expressed in terms of the operations, sums, products, roots, compositions. Essentially, these are all of the operations we've been working with since algebra. You might say, okay, there's no differences in there. Well, that's a sum, right? Now, there's no quotients in there. Well, that's a product of 1 over something, and roots. And so these are all of the basic functions we've been working with since algebra. Okay, so an elementary function can be expressed in terms of these operations on finitely many, that's an important word there, polynomial functions, rational functions, trigonometric functions, hyperbolic functions, exponential functions, and possibly their inverse functions. Okay, so basically an elementary function is one that can be expressed with the basic operations on finitely many, I call them high school functions. These are functions you learned since high school, even working with them. In fact, all of the functions we've been working with from Calc 1, nearly all of Calc 2, except for when you got to series, maybe you did some, and in Calc 3, and in this class, they've pretty much been elementary functions. For example, all of these are elementary functions. The reason being is because I can express them using the basic operations in terms of finitely many of these basic high school functions. So x squared, that's a basic high school function. That's a basic high school function. You can see there's a composition in there. There's a quotient. There's a natural log in there, which is the inverse of exponential. There's a difference, squares. So also this one, of course, you'd want to evaluate the derivative. But if you evaluated the derivative of e to the tan x, you get e to the tan x secant squared x. And if you think about that function, that is an elementary function, right? And even this one, integral of cosine x dx, well, that's just sine x. And that's a basic high school function. So, but not all functions are elementary. There's some that we've been kind of avoiding. We avoided throughout Calc 1 and probably all of Calc 2, but your teacher might have mentioned this towards the end. Maybe they threw some of these in, but for example, something like this one, that is a non-elementary function. And you might say, wait, can I just integrate that and then I'll get an elementary function? Well, you could try, but there's no antiderivative that you can express in a finite way. Okay, same with this one. Like if we ever ran across these integrals before without using series, we can't really do anything with them. They're kind of stuck because you can't express them in a finite way. So unless you're working, at the end of Calc 2, there's really nothing you can do there. So how would you write something like that? Well, these are called non-elementary functions, and these can be expressed in an infinite way. And the way we do that is with power series. Okay. All right. Any questions on that so far?
Oh, no, that sounds good.
Okay. So what is a power series? Well, the first section, 8.1, it was kind of an introduction. We kind of throw you in and talk about Taylor series, but this is kind of the bigger picture. Power series is a more inclusive series. So a power series, you always talk about its center, x naught, just like the Taylor series. It's an expression of this form.
You can find that in your Apple Music library. You can ask it to play a radio station or ask for your music on a different app.
Stop. Stupid Siri. Okay. So that's what a power series, it has that form. And if you expand it out, it's gonna look like this. So what you want to notice is it's got all these x minus x naught factors in there. Each one has an x minus x naught. And the powers are going up by 1. There's also an x minus x naught factor there. It's just x minus x naught to the 0. And then you've got these coefficients sitting in front of each of the x minus x naughts, which are just constants. Okay, so those change and those will have some values that we assign to them. Okay, so that's what a power series is. Now, you'll notice a power series is different than a regular what we called series before, or series of constants. And what makes it different is it's got this variable x involved. Okay, so so you might ask, okay, well, this is a different object. So how do we talk about convergence? Well, if you think about it, we would say that a power series converges at a point if once we plug in that point, which is a constant, let's say c, if we plug it in there, it becomes a series of constants. Those are all constants there. And once it becomes a series of constants, you can apply the series of constants test, right? So we can determine convergence at a point and divergence at a point, right? So if it converges, we say the power series converges, at C. If it diverges, we say it diverges at C. And then the idea with power series, though, is you want to find an interval of convergence. It's kind of weird. You might wonder, why would it be an interval? And it turns out it just is. I don't know if we go through the proof of that, but it turns out that power series will converge on these kind of symmetric intervals everywhere inside of this interval, and then outside of it, it'll diverge. Okay, so we'll talk more about that in a minute. But the largest interval for which a power series converges, it's going to be about the center. It's called its interval of convergence. So just like a Taylor series, remember I used this terminology. I mentioned that a Taylor series is basically an infinite degree polynomial. And that's what a power series is, right? In fact, a power series is just a more general case of a Taylor series. A power series is where, I have these constants, and these can be any constants sitting in front. So the ANs can be anything. But a Taylor series is the special case where the constants have to be those guys. Okay. So put simply, power series is more general, and a Taylor series is a specific type of power series. Is that okay?
Yeah.
Okay. All right. So let's investigate this interval of convergence. These would be all the points where the power series converges by plugging in points and figuring out using the series of constant stuff. So basically, for what values of x does a power series converge? Well, the first thing to note is that a power series is always going to converge at the center. Okay. There's a reason, by the way, why we call it the center. It's because when the series does converge, it'll always be on symmetric intervals about the center. So the way you could prove that it's any power series is convergent at the center is by simply plugging in the center. So if you took x naught and you plugged it into the general form of a power series, you'll notice what happens. All of these guys drop off because they become 0, but you're still left with the first constant term, a naught. And so that's a finite number. So that means that your power series converges to a naught. That is the sum. All right, now, a power series can converge at other points other than its center, but it kind of depends on these constants, what they are. That will determine where it converges. So a useful fact, I mentioned this earlier about power series, is that when power series converge on intervals, they're always symmetric intervals about the center. And for now, I'm going to ignore the endpoints. But if this is the real line, and let's say the center is at x naught, when the series does converge, it'll be symmetric. So the distance, like it'll converge everywhere over here and everywhere over here in a symmetric way. Now, as far as the endpoints go, we'll talk about that later. But before we get to that, this kind of leads us to the idea of talking about the radius of convergence of a power series. And we use the term radius because this is kind of like a one-dimensional ball, right? It's like a flat ball or flat disk. So we can talk about, this distance being the radius. So perhaps there's something, perhaps there's a way that we could find the radius of convergence. And if we could find that, then at least we'd get this, at least we'd figure out kind of how wide the thing is. Of course, we wouldn't know at the endpoint whether those endpoints are convergent, but we would know it's convergent inside and we know it's divergent outside. And then we'd have to test the two endpoints separately. So there's this theorem, radius of convergence theorem, which basically says is that if you have a power series, its radius of convergence, well, it's kind of what I was just saying above about how they always occur on symmetric intervals. The radius of convergence, usually we designate with the Greek letter rho, and we're going to let rho be a value anywhere between 0 and infinity. So it's non-negative, and also rho can take on, infinity is not really a number, but we'll use that convention that we mean goes off forever. And so the power series, do you remember the term absolutely converges? It's a different type of convergence.
Yeah.
Okay, yeah. So absolute convergence is it's actually it's a type of convergence that's actually stronger than regular convergence. So if you have absolute convergence, you get regular convergence for free. But in any case, what ends up happening is that the power series will converge so long as the distance between x and x naught is less than rho. By the way, that's what absolute value means, right? The distance between x and x naught. So since x naught is the center, what I'm saying is that x can be no more than, has to be less than a radius of rho away from x naught. And it diverges outside of that interval. So that means the distance between x and x naught is greater than rho. That would be the divergent case. So now, if your power series converges for all x, every value you plug in for x, here the thing converges, then we would just use the convention and say that rho equals infinity. Although infinity is not a number, so technically it doesn't make sense to write that, but that's the convention we use. And then if the power series only converges at the center, which is a fairly useless power series, by the way, then we would say that the radius of convergence is 0. Okay, so here's the idea as far as what the things look like. So, your radius of convergence, if this is your center, worst case, it's going to converge at the center there. And then best case, it converges everywhere. And then maybe something in the middle. And of course, rho would be the radial distance. And you'll notice I'm ignoring the endpoints for right now. I'm just looking at the inside and the outside of those endpoints. Okay. And then, absolute convergence. Basically, this series is absolutely convergent. This is just the definition. If the series of absolute values converges, and you can prove that that's stronger than regular convergence, but we won't worry about that again.
And that's, sorry, for absolute convergence, like when I was like in Calc 2, it was usually just for alternating series, right? Or does it have anything to do with other type of series?
Well, yeah, it doesn't necessarily, it could be any, I mean, if the terms are all positive, then absolute convergence is regular convergence, right? Because it's the same series. But so the neat thing about what is it called? Absolute convergence is that with a series that's absolutely convergent, you can rearrange the terms because you're adding a bunch of terms together, right? So you can rearrange the terms in any order and you'll get the same sum.
Mm-hmm.
But with a series that's regularly convergent, you can rearrange the terms and get basically whatever sum you want. If it's you can, maybe I said that wrong. You could get different sums. If it's an alternating series, if there's an infinite number of negative terms and positive terms, I'm not positive about this, but I think you can get, I was actually just talking to Jack about this the other day. You can get any sum you want. So it has to do with rearrangement of terms, if you want to know more about it, I'll have to go back and read about it again. But for now, we're using this theorem, but you can kind of ignore that it says absolutely there. It's
Okay.
just it's stronger than we need, so we can just use it. But there is some interesting aspects about absolute convergence compared to regular convergence. Okay, so so now that we know what the radius convergence is and kind of what it looks like, it's always on symmetric intervals about the center. How do we find that radius, right? So the trick here is to exploit one of the series tests, the series of constants tests back from Calc 2. And we're going to use the ratio test. It doesn't have to be, but this is the typical one we exploit. So let me just review what the ratio test is for a series of constants. So here's a series of constants, right? There's no x's in there. So for the ratio test, what you do is you compute the limit of the absolute value of the n plus first term over the nth term, and I'm talking about the actual terms, not the partial sums. And then you find that limit r, and if r is less than 1, then the series converges. I'll just say converges because absolute convergence is stronger. And if r is greater than 1, then the series diverges. And if r equals 1, then the test is inconclusive. So you have to figure it out another way, maybe use another test. So here's the thing, though. That ratio test was specifically for series of constants. But we'd like to use this on a power series, which involves a variable. So we can't really use it directly. However, for any given value of x, if I were to pick a value of x and plug it in, then it does become a series of constants, and we could apply the test, right? So what we're going to do is kind of we're going to force this conclusion, the first one, for the ratio test to work. We're going to basically look at our power series, okay, and we're going to say, okay, for any given x, I'm going to take the limit of the n plus first term, the absolute value of the limit of the n plus first term over the nth term. That's this. So I'm applying this, assuming I've picked x already, right? And I'm going to take the limit. And what I'm interested in doing is I'm trying to figure out where it converges. So I'm going to set it less than 1. Okay, I'm going to force it less than 1. And then what I'm going to do is I'm going to rearrange the left-hand side and see if I can figure out what x has to be, where x has to lie in order for this to happen. So if you take the left-hand side, these are just constants. So we can take them out. Of course, they could be negative, so keep the absolute values on them. I'm still evaluating the limit on the entire thing. And then let's see. Well, this guy, we've got x minus x naught. We've got n plus 1 of them upstairs and n downstairs. So we can cancel a bunch of those. And now look at this. I'm really interested in getting at what x has to be in order for this thing to converge. So I want to move this to the other side because I really want to get at what x has to be. So if I move this to the other side, this is a positive number. If I move it to the other side, then I'll get this. Is that okay? I don't have to switch the sign because it's positive.
Right.
And I guess it could be 0, but that would be it. No, let's see. N plus first term over n. No, it won't be 0. Yeah. No, it will be positive. Okay. So then what we could do is we could take this guy and just use some simple algebra to kind of rewrite this thing. So if you look at the right-hand side, the top's 1, that's positive. So, and we could pull the limit out. We could write it this way. And then, that's just a complex fraction. We could rewrite it this way. So notice what's happened is the an and the an plus 1 have switched places. Okay, so what's happening here? So now what we're saying is that the power series will converge so long as this is less than this. In other words, so long as that happens. So what I'm saying here is that so long as the x that you use is within this distance from x naught, then the power series will converge. So what does that mean? That means this is the radius of convergence. So if we just set that equal to, let's call it L or rho or whatever, I mean, probably should have used a rho there, it doesn't matter. That is the radius of convergence. So that's how we're going to find it for a power series. So this is confusing for people a little bit because they're probably thinking about the ratio test and they remember it this way to find the radius, right, with the n plus 1 over n. But because we can't use this directly, you have to make this argument, and the radius is actually flipped, if that makes sense. Okay. All right, so that's all that is. So basically, once you find the radius, you'll know this distance, and you could draw it graphically, something like this. It'll converge at the center and on some radius. And, we haven't talked about the endpoints, but we know everywhere inside the endpoints it'll converge and everywhere outside it'll diverge. Now, finally, the goal is to talk about the interval, and the two pieces of information we're missing are those endpoints. So you have to test those, and usually we do that at the end. So, but that's easy. That's just two x values, two constants for x. So you would just figure out what they are, and then, plug them in, do a series test on each of them, series of constant tests on each of them, which you can do using Calc 2 methods. And then once you got that, the entire interval, you'll know where it's convergent and where it's divergent. So that's the idea. Is that okay?
Yeah.
Okay. All right, so let's take a look. Here's a power series, and where's the center of that guy?
X equals 3.
Yeah, yep, the center is 3. So we know for sure it'll at least converge at 3, right?
Mm-hmm.
In fact, if we plug in a 3, we can see that it'll converge to 1. But hopefully it converges more than that, an interval larger than that. So let's first find the radius of convergence. So the radius of convergence is found by finding that limit, right?
Mm-hmm.
Okay, so you'll notice that the ANs right there, these are the ANs sitting in front. So it's very similar to what we did before, but we're using the coefficients and you flip it upside down. It's not quite the ratio test, it's the opposite. So anyways, if you evaluate that limit, I'll let you work through that. You did a lot of this in Calc 2, you end up getting 1/2. All right, so what that tells us is that the radius is 1/2, so that's it. So you should be picturing the point 3, and then you're going to go out a distance of 1/2 up and 1/2 down, 3.5 and 2.5 to 3.5, and there's at least your starting part. We still have to test the endpoints, right? Okay, but that's the radius. And then part B, find the interval. Okay, well, to find the interval, you need to test the endpoints. It's essentially what I'm asking you to do because we already got the radius. So there's 2 points, right? There's 2.5, which is that one, and 3.5, which is that one. So we simply plug them in. So if you plugged in, let's say 5/2 into your, where are we?
Into the top right for X.
Into the power series right there.
Yeah.
5/2 minus 3, so that's -1/2 to the n, and then you'll have to play around with the indices and get negatives to cancel and stuff. But what ends up happening is you'll end up getting this series of constants, right? And then you want to ask yourself, does that series converge? And then you'd have to go back to your knowledge of calculus 2 and make an argument to figure out whether or not that one converges. That one diverges by the comparison test with the harmonic series, but there's other ways to prove it as well. That one's probably you could use limit comparison, you probably use an integral test, but yeah. This one here converges by the alternating series test. That one, if you remember, basically if the terms alternate and if the absolute value of these guys, if that sequence goes to 0, 1 over n plus 1 goes to 0, then you're guaranteed that the series will converge by the alternating series test. So we got divergence here and convergence there. So there's your interval of convergence from -5/2 to 7/2. So we know everything outside of that diverges and everything inside of it converges. that okay?
It should be positive 5 halves, right?
Yeah, it should be. Thank you. All
Okay,
right.
yeah.
Yep, you are correct. Okay. All right. So that is interval of convergence. And then it's important to just note that a power series is indeed a function. Um, it's a function on its interval of convergence, right? It only makes sense on its interval. That's the only thing where you'd get it. It's the only interval values for which you'd get out values. Like for example, here's a power series. This is a geometric power series. You can show that this geometric power series converges on the interval -1 to 1, and it diverges everywhere else, including the endpoints. You prove this in Calc 2. You might want to go back and look how you prove something like that. But so if you wanted to graph the interval of convergence, it would look like that. So what does this mean? This means that if you stay in that interval and you pick some value, let's say x equals 1/2 or something, and you plug it in this thing, it's going to pop out a value. Well, that's what a function does, right? A function, you give it a value. It's a rule that assigns to each input and output. So as long as you're in here, every time you give it something, it's going to pop out a value. So that's what a function is. So essentially, this is the domain of this power series function. That's what we're finding here, the domain of the power series function. And then interestingly enough, for this one, you can actually write this power series differently. You can actually write it like this. There's an argument to prove that. There's a real fun algebraic one, which doesn't require calculus at all. It's a little finicky. It's not exactly an airtight proof, but it gets at the idea. But if you want to look that up, proof of geometric series expansion or something like that, you can see how it works. But in any case, yeah, so you'll notice that this function right here, which is an elementary function, right?
Yeah.
This function can be expressed as a power series, which is an infinite degree polynomial, like in an infinite way. And the idea here is that we're going to have more complicated functions, let's say like sine x squared, that you can express, that you can do the same thing. You can write it this way. The thing about sine x squared is that is the integral of sine x squared is that you can't, that is a non-elementary function, but you can express it in terms of an infinite degree polynomial.
Mm-hmm.
Is that okay?
Yeah.
Okay.
So
yeah.
That the 1/1 minus x is where the like expressing functions as a power series, like how they would use r, but they would say 1/1 minus r. This is the same thing, right?
Yeah, same thing.
Okay.
Yep.
Okay.
Yeah. All right. Algebra. Okay, so this is a real nice and easy section because basically the algebra of finite degree polynomials, the ones we've been working with in algebra forever, those properties basically carry over to infinite degree polynomials. So like, let's do this one first. Sums. So yeah, we'll come down here. So you know how we add, multiply. I could just say sum and multiply since you get division for free. Well, no, I could put it in separately. That's the way I have it written. Doesn't matter though. So let's say we have two power series. Both of them have center x0, so they're both being expanded about the same point. Let's say that each of them have a positive radius of convergence. That's important to note, right? Okay, so that means that they converge at the center, but also there's at least some small open interval around x0 for which both of these series converge. I guess I should have just used one since it's the same point x0. Okay, so when this happens, you can sum them together. So if you wanted to add the two functions together, all you would essentially do is you'd add them like a regular polynomial. You'd add like terms. Mm-hmm. So since these guys are like the x minus x0 to the n, x minus x0 to the n, essentially you're just adding the coefficients. which is what you do for regular polynomials. Okay. And as far as the interval, it's usually the common interval. However, you probably don't want to get into this, but it can be larger. You can get things to cancel in a way that you can actually expand the interval. Don't worry about that.
Okay.
Invariance. And then for products, if you want to multiply the two functions together, you would do it the same way that you do it using finite degree polynomials. You take every term in the first polynomial times every term in the second polynomial. Like if it's a binomial, you use FOIL, but if it's a trinomial, even higher. I don't know why I did that confetti thing. But in any case, you do the same thing here. And if you run through all the combinations, basically you're going to get this formula for Cn. If you want to do it for the finite case, you can make this argument why this would be true, and then you just extend it to the infinite case. And then for quotients, you can divide these guys. It's a little trickier though. There's no like nice formula for this. But typically the way we handle this is we use kind of multiplication in reverse, or we can just use long division like we do with polynomials. So we will run across some of these as we progress. And then the other property that carries over is this one. So let's say that you have a polynomial equal to 0. And in this case, let's make it an infinite degree polynomial, and it's equal to 0. Well, if I gave you a polynomial with coefficients that I didn't know what they were, and I said, well, this polynomial is equal to 0, you know that all of the coefficients have to be 0, because both it's like when we did undetermined coefficients, right? So
right.
Essentially what that means is that each of these guys would have to be 0. You can equate like terms on both sides, essentially, and the coefficients on both sides. Okay, so we're going to actually use this a lot. So it'll feel pretty natural. But the important thing to note is the algebra pretty much carries over from finite degree polynomials. All right, and the calculus. So this is interesting and actually quite fortunate, because let's say that you have a power series for a function f. Let's say it looks like this. And what this is saying is that it's convergent on an open interval about x naught with some positive radius of convergence. So it might be really small, but there's some positive open interval around x naught for where this converges. By the way, you kind of need this in order to talk about differentiability, right? Because if you're at a single point, like if rho was 0, or no, I guess you can't even say that, because there'd be no solution there. But let's say this converged just at the center. You can't really talk about differentiability, because you need to have an interval, an open interval, to talk about different. You have to take a limit on both sides for differentiability.
So okay. If it's just a point, there's no, you can't differentiate.
Yeah, like if I gave you the function f of x equals 3 if x equals 1, and everywhere else is 0,
mm-hmm.
and then I ask you to differentiate the function at 1, like you can't. It's just a point.
Right.
It doesn't do anything for us. You have to be able to have a limit. So you need, in order for us to talk about this theorem, that radius would have to be positive. You have to have some open interval, which, by the way, once you have that interval, there's an infinite number of points. It's in that little interval, because you can always zoom in and make it look big. It's called a continuum. It's essentially a bunch of numbers packed together so tight that you can't even count them.
Mm-hmm. All
right. So let's say that we have that function with some positive radius convergence rho. Sorry. Okay. So what that means is if you do have this thing with some positive radius convergence, it means that it's differentiable and integrable at the point around that point x naught, and the radius of convergence. And actually, probably should have wrote that down below. Oh no, we're okay. They're differentiable and integral, and here's what the derivatives are. And it's really easy to find these, because essentially all you're going to do is you're going to differentiate the power series and you're going to treat it like a polynomial. It's infinite degree. So you just differentiate how you normally would a polynomial term by term. So this a naught there disappears. The derivative here becomes a1. This becomes 2a2 x minus x naught, and then 3a3 x minus x naught squared, so on and so forth. But what's interesting about this is not only can you take the derivative so easily, just treating it like a polynomial, but the radius of convergence actually stays the same. Okay. Now I'm ignoring the endpoints, right? So that's a separate issue. We don't even need to talk about them because you need to come in from both sides. But as far as this radius, it'll stay the same. The other thing is that you can integrate. When I switch that to a G, you can integrate F. So you would just integrate term by term. So if you were to write all these guys out, and you integrated, let's do, okay, the first term. Now, this isn't exactly straightforward what's happening here, but the variable is x, or you can think of it as x minus x naught, where x naught is just some constant, doesn't matter. So x minus x naught to the first over 1, and then a1, that'd be x minus x naught squared over 2, and so on and so forth. Is that okay?
Yeah.
Okay. I just wrote that in to satisfy the pattern.
Yeah.
But, that's a constant. So it really is a naught x, and that constant would be absorbed on the end. So all these constants are taken care of. Okay. So that's pretty much it. So it's pretty straightforward, actually.
Yeah.
So for example, let's take a look at this guy. So we've got, let's say we have this given geometric series. Here's the interval of convergence. Typically, we write the interval on the right side of our expansions. So what I'm saying is that this function is equal to that power series on this interval of convergence. And you could write it this way, -1 to 1, but it doesn't matter. All right, so we're going to use some of what we learned above to do these expansions. So let's say you wanted to expand that power series. I'm sorry, that function as a power series. So you can actually use known power series expansions on intervals. Since these, hey mom, I'm sorry. It's hard to concentrate. It's okay. All right, no problem. My mom likes to sing. So what we can do is you just do a little substitution. So since this is a function, what we can do is we could let's say replace x with -x, or maybe -x squared, and just replace everything in there, including the interval of convergence. And we'll have to manipulate that to see how it changes the interval of convergence, but in this case it won't. So if we wanted to find a power series for that guy and find its interval of convergence, we could use a known power series expansion on a known interval. Just plug it, plug in -x squared right there and everywhere else. Simplify like so. And then I'll let you work through the details. I don't think it's really going to help for me to go through the details. And then this guy over here, you're replacing the x with -x squared, right?
Mm-hmm.
So you can actually, I mean, you might be able to make this argument in your head, but what you're saying is that has to be less than 1. Well, that means that has to be less than 1, which means that has to be less than 1, which means that has to be less than 1. So in this case, it just so happens that interval of convergence is the same. So you would take this and you would write it over to the right up there. You write it right there. Yeah. Yep. Okay, so that had nothing to do with derivatives. That was simply plugging in using a known power series expansion. But this one over here, so if you wanted to find a power series expansion for this one and you wanted to use this, you'd have to come up with some relationship between this function and that function. Mm-hmm. And you might notice that if you differentiated this function, you do get that function. Right. So Okay. So what that means is if we want to represent that function, we should just differentiate our expansion for 1 over 1 minus x. By the way, when we're done, the interval, the radius isn't going to change. It's still the same. So the interval doesn't change. So we'll go ahead and differentiate term by term, and it's valid on the same interval. Is that okay?
Yeah. Yeah.
And
so
then
you only have to worry about the interval changing if you substitute something.
yeah, yep,
Okay.
yep, yeah, yep. And then for the last one, 1 over 1 minus x and arctan of x, you want to find a relationship between the two. So there's a few ways notationally how you could do this. I like to write it this way. You know, if you notice the right-hand side, I've got an integral. I'm integrating with respect to t, but I'm evaluating from 0 to x. So once you integrate with respect to t, you know, you get a function of t, but then you're going to plug in t equals 0 and t equals x. So in any case, you know, you don't have to write it out the same way I do, but this is the way traditionally I like to write it. So yeah, we're going to integrate this function and evaluate from 0 to x. So if we integrate, let's see, 1 over 1 plus t squared, which, where did I get that guy? Oh, I'm just replacing, let's see, this guy with, oh, it's just part A. Yeah, this guy. So we already did the work in part A. Of course, it's an x, so I would just replace it with a t squared.
Okay, yeah.
Okay, so that's there. And then we evaluate from 0 to x. And now we have our series expansion. And since it's just an integral, we haven't changed the region of integration, the interval of convergence. Yep. I'm getting my Calc 3 mixed up. Is that okay?
Yeah.
Yeah, you'll work through the details. I just think it probably better to do that on your own. All right, almost done. Okay, changing and shifting indices. So this part's actually really important and probably one of the parts that's going to trip up a lot of people. We want to get comfortable, really comfortable doing this. So the first thing to note is that the index, this is the index right here, that variable of summation n. It's usually an n, but sometimes it's an I or a J or a K or something like that. But in essence, it's really a dummy variable. That's actually a technical term. Have you heard of that term?
Yeah, actually.
Okay. Yeah. So like f of x equals x squared. That's a function, f of x equals x squared. And you might ask, well, is the x important? Well, I mean, what is a function? It's a rule. Okay, what is the rule? It's taking in something and squaring it. It doesn't have to be an x. It could be, you know, a y, it could be a z, it could be a cat, it could be a square, you know. So whenever you're working with a function, you're working with dummy variables. Now, the reason we typically use an x is because if we don't have some convention for everyone using an x, then it would be really hard to compare all of our work, right? So usually the input variable is x. So same thing here, you know, we have our kind of standards for what we kind of want to choose, n, j, k, you know, n's a popular one, but they are dummy variables. You can change the names. All right, so what does that mean? Well, that means that we can just switch out the names whenever we want. So we could take this series and we can rewrite it that way or that way. Is that okay?
Yeah.
Okay. And then the next thing to note is that we can always re-index or shift the variable of summation without actually changing the sum at all. Just requires, you know, just be a little careful. For example, okay, so this general power series right here, we could shift it. We could shift and rename essentially. I could start it off at k equals 1 to infinity. You'll notice that some of this changed over here.
Mm-hmm.
That n became this, and then n became this. Now, it's easy to check that this works because you could just simply look at the first few terms. So if you plugged in an n equals 0, and then an n equals 1, and an n equals 2, and looked at those terms, and then did this one and plugged in a k equals 1, start off at 1, right? And 2 and 3, you'd see you get the same terms. And then same with this one. The variable names are dummy. It doesn't matter what they are. But this is just indicating that it is possible to reindex. And I'll be kind of showing you how to do that in just a minute. But is that okay?
Yeah.
Okay. All right. So let's say we have this power series, and what we'd like to do is rewrite this power series so that the generic term for the power function, this is the power function I'm talking about. We want it to be x to the k instead of x to the n minus 2. This is a common thing that you're going to want to do when we get to the power series method. You're going to see a bunch of this. You're going to see it and it's going to be off and you have to fix it. So it's x to the k. So all you really have to do is basically do a change of variables, essentially. Let k equal n minus 2, right?
Mhm.
So, oh, before we do that, this is interesting. Take a look at the first term there. When you plug in a 0, do you see that it disappears? And then do you see if the next term n equals 1, you see that disappears too?
Yeah.
So really, is it safe to say we could start this thing off at 2 without changing anything?
Yeah.
Yeah. So we'll clean it up first and we'll write it this way.
Okay.
All right. So we're going to replace the k with n minus 2. So we just let k be n minus 2.
Cool.
Well, if k is n minus 2, this comes along with a lot of equivalencies. That also means that n is equal to k plus 2. That means n minus 1 is equal to k plus 1. And it means if n equals 2, then k equals 0. It means a lot of things, right?
Mhm.
Okay. All right. So for example, here. Okay. So we're going to rewrite that. So that n minus 2 becomes a k. That n minus 1 becomes a k plus 1.
Mhm.
And that n becomes a k plus 2. And that n equals 0 becomes a k equals negative 2. I think that's what I was trying to say over here. Same thing. Is that okay?
So where does the -2?
Well, if n
Oh,
equals
so
0,
okay, yeah, I see.
if n equals 0, then k equals negative. All I'm doing is, normally you wouldn't write this out. You could just figure this out in your head. Just
Okay, yeah, I see.
all right. Now on the right, it looks a little uncomfortable, right? Because we're starting off at a negative index.
Yeah.
And it's technically okay to start off at a negative index as long as there's no issues. But what you will notice is that if you plugged in a k equals negative 2, you get a 0 on that first term, right?
Yeah,
And if you plugged in a negative 1, you also get a 0.
right.
So
Okay.
actually, we could start this thing off at 0, like so.
hmm
So now what we've done is we've taken the original power series and we've kind of re-indexed it and renamed it too from n's to k's with a general power term of the form x to the k.
Okay.
But okay, okay.
Yeah, so can you go down though? So for the n, it zeroed out, so it didn't matter, but for that n on the left at the bottom, you put it up to 0 and then you just have to balance it by subtracting 2 from that exponent there, right?
Are you saying going from here to here?
Yeah, just the n part, just to check, because you would have n equals -2. So if you add 2 to that, you go up to 0 for the index.
Say that one more time. I'm kind of missing.
So the series on the left that you have highlighted.
That's the one I started with. Yeah.
Oh, okay.
Yeah.
Okay.
Maybe I made that unclear.
Okay, I see. Yeah.
That's what I really meant. Yeah.
Okay.
Yeah.
But so basically, like anytime you add to the index, you have to subtract that from the
Yeah. Yeah, I mean, it's just a relation between n and k.
Okay, yeah.
So if one, if one changes, the other one's going to change. So if you subtract two here, the other one's going to be two higher. So
Right. Okay. Yeah.
okay. And okay, how about this one? Show that this polynomial times that series, power series, is equal to that power series. Okay. Okay, so when you want to, show that an equation's true, oftentimes what we'll do is we'll start on one side and try and get to the other. So
Mhm.
we'll take that approach. So let's start on the left. So if you start on the left, and I highlighted the things I wanted to focus on, the x cubed and the x to the n, we can actually push this x cubed into the series.
Right.
I know it's uncomfortable sometimes for people to know when and when you can't do that, even for integrals and even for limits. But all you have to do is ask yourself, is this a constant as far as this is concerned? The variable here is n. So this isn't going to affect anything. You can push constants through. Same
Right.
thing with limits, same thing with integrals and derivatives. So essentially it's a linear operator. So we'll push the x cubed through. So it looks like this. So it doesn't look like we've gotten too much closer, but at least it's a single series now. All right, so then let's see. We're trying to get to here. So let's do this. Let's let n plus 3 be k. Now I set it different. It means the same thing.
Okay, that makes sense. Yeah, that's what I was curious about. Um, yeah, because I was reading through and it said let n equals k minus 3. Okay.
It's the same thing though, right?
Right, yeah.
Depends how you
Makes
say it.
that's clear now. Yeah, okay.
This is more clear. All
Yeah.
right, so that's going to change that to a k. And then you can kind of do this in your head, right?
Yeah.
That's n, and that's k minus 3, n minus 2. So let's see, we subtract 5 from both sides. Okay. And then n, subtract 3. So that's k minus 3. And then we're shifted up 3 units. Yep, there we go. So now we're really close. So now the only thing left is, this is in terms of k, but that's n. But remember, this dummy variable. Indices are dummy. So
Mhm.
just replace the k's with
Okay.
it. Okay. All right. I would suggest using different variables like I have. I switched to k's. I've seen students try and stay in n the whole time, but then you're going to get confused on which ends are which ends. It's better just to switch to a new variable, k, do the shifts, and then go back to n at the end.
Okay. Yeah.
Yep. And this one, show that this identity is true. So we got a power series plus a power series equals 0. And we're going to show that those guys equal 0. And
Yeah. I mean, I worked through this on my own, so you don't have to
okay.
go through it. You don't want to.
All right. Yeah, I think I'll let the rest of the class do that too. I think I wrote in good enough explanations for you guys to work through it.
Mhm.
Yeah. Okay. All right. This is fairly important though, because we are going to do this a lot later on. Okay. All right. And lastly, well, mostly lastly, analyticity. So this is a new topic. So I've used this phrase analytic before, and I've kind of used it roughly. I think I've used it with you guys. To mean that you can express the function in some, using math basically. But the word analytic has a specific meaning in mathematics. So we say that a function is analytic at a point x naught if the function is equal to to a power series on some positive radius convergence about that point. All right, so going to bed. Going to bed? Okay. 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 All right. So when you hear the word analytic, you think, oh, it can be represented as a function and the radius convergence is positive. That means there's some radius. It's more than convergent at the center. It's got some radius around it. Even if it's really small, it's got some radius. All right. So yeah, not all functions are equal to their power series expansion. So only some functions are strict enough to where this happens. So let's take a look at this one. So f of x equals 1 over 1 minus x. This function is analytic at 0. We'll just say 0. And essentially what I'm saying is, I'm saying that this does have a power series expansion at 0 that's valid on some positive radius convergence. In fact, we know what it is. We were just talking about it earlier. There's a power series expansion, and it's centered at 0, and the radius happens to be 1. So proof by, we already know that's there, right? Proof by calculus 2, I guess. All right, so when we use the term analytic, if I say a function is analytic, that means that you can write it as a power series, essentially. All right, and we're going to be using that. We're going to be saying this moving forward. So whenever I say that, that means you can write it as a power series and there's some positive radius convergence. So here's the good news. There's a bunch of functions we work with where we don't have to really prove analyticity. We can just assume it. So for example, polynomials, those things are analytic everywhere. If you want to find a power series expansion for this function at 0, go ahead. It's easy. In fact, this is it. That is the power series expansion. You might say, but wait a second. I thought a power series has an infinite number of terms. Well, it does. There's a plus 0, plus 0, plus 0, so on and so forth, right? Mm-hmm. And this one happens to be centered at 0. Now, you could rewrite the thing so it's centered at 1. You'd have to rewrite all these so they had x minus 1s, right? Mm-hmm. So polynomials, by their very nature, are analytic everywhere because you can always just, rewrite them so they have a new center wherever you want. All right, rational functions, those things are analytic on their domains. So this guy has a power series expansion with positive radius convergence everywhere except at 1 and -1. It kind of makes sense why, because if the function's not defined there, you can't possibly it wouldn't be defined at the center. It's impossible. So there's no point in trying to find one. Transcendental functions, these are all our functions that aren't built with, our standard operations. These would be things like sine x, e to the x, natural log of x, inverse trig functions, and stuff like that. These functions are also analytic on their domains, and we'll just take that as a given. So all of these, we don't have to prove or anything. We'll just take those as a given. Also, if you know that f and g are some functions that are analytic at point, then f plus g is analytic, f minus g, f times g, and f over g are also analytic. Also, constant times f are analytic. All right, so this is going to help us a lot. And then if you want, you can read through that example there. Mm-hmm. And then also, if f is analytic at a point, that means that f is infinitely differentiable at that point. And all of the derivatives must be analytic at that point. To kind of speak more broadly about this, I kind of made this little picture to kind of illustrate the desirable qualities we've been kind of working through since Calculus 1. So I remember back in Calculus 1, probably we first learned limits, but then we looked at functions and we saw that some functions are continuous, at, let's say, a point. And that's a desirable quality to have, right? Continuity. And then we learned about differentiability, right? And we'd say, okay, differentiability at the point. One of those is stronger than the other, right? One of them is more desirable, I would say. Do you remember which one that is?
If it's differentiable everywhere.
Yeah, if a function is differentiable at a point, it means it's continuous at a point. You kind of get that for free.
Right, okay.
And kind of think of it like a hierarchy of of desirability. So if you have a function, some functions will be continuous at a point. All right, not all of them, but some of them will. So that would be everything in the blue circle. Now, out of all those continuous functions, some of them will also be differentiable at that point. But we could go in reverse and we could say, if a function is differentiable at a point, it's automatically continuous at a point because it's inside the set.
Right. Okay.
Differentiability is stronger than continuity. In other words, if we've used this theorem throughout Calc 1, 2, and 3, if a function is differentiable at a point, then it's continuous at the point. We've used it throughout our studies. All right. Well, what would be stronger than being able to differentiate one time? Well, 2 times. If you have a function, you can differentiate it twice. That would be more than once. That's more desirable. Now, it turns out there's lots of examples of functions that you could differentiate, let's say twice, but you can't differentiate the 3rd time at a point because it's undefined. I don't know if I gave you one. Oh, like this one. Okay, so like this function. This function, it's finitely differentiable. If I try differentiating it 1 time, I get this guy. 2 times, I get this one. 3 times. Okay, so I should say it's infinitely differentiable. However, the 3rd derivative does not exist at 0. And that's because of this problem right there, right?
Mm-hmm.
All right, so all I'm saying here is when you're differentiating, it would be desirable if you could differentiate at a point as many times as you want, so off to infinity. So this would be our next desirable quality would be which functions are infinitely differentiable. For example, x squared is infinitely differentiable at 3 because the first derivative is 2x, plug in a 3. The next derivative is 2, plug in a 3. Next derivative is 0, plug in a 3. Next derivative is 0, plug in a 3. Next derivative is 0, plug in a 3. There's no problem, right? So infinite differentiability would be even more desirable, and it's harder to be infinitely differentiable than it is to be finitely differentiable, which is harder to be continuous, which is harder to be a normal function. This is our hierarchy of desirable qualities in functions that we've been kind of progressing through. The last one, this is kind of the pinnacle or the apex of desirable functions. This would be analytic functions. If a function's analytic at a point, then you get everything else for free. If the function's analytic at x naught, it means it's infinitely differentiable at x naught, which also means it's obviously finitely differentiable at x naught, which also means it's continuous at x naught. All right, so this is kind of the best well-behaved types of functions that are analytic, and these are functions that can be expressed as power series with positive radii of convergence. I'll let you work through any of the details in there that I go through if you're interested. All right. Is that okay so far? We're just about done. We have 2 more minutes.
Yeah, sounds good. Okay.
And lastly, Taylor series expansions. So if you've got a function that's analytic at a point, in other words, we know that it has a power series expansion with some positive radius convergence. So we know this. Well, by theorem 4, we know that the derivatives, all the derivative f will have a power series expansion in x naught. This is the theorem. You can look at it if you want later on. But we know the derivative will exist and it will have a power series expansion and it'll have the same radius convergence. But now you have a new function which you could apply the theorem again and you can just keep bootstrapping it. So essentially what that means is you can differentiate the thing ad infinitum. So there's the 0th derivative. Here's the first derivative. And you'll notice that I changed this n equals 0 to n equals 1 because the first term disappears. If you plug in a 0 there. Same thing with the rest of these. I just switched it over. First couple terms disappear, 3 terms disappear, so on and so forth. So if we plug all these in, if we find all these derivatives, and then we evaluate all of the derivatives at the center. So if you plug x naught into the first one, you'll get a naught. You plug x naught into the first derivative, you get 1 times a1 and this guy. And this pattern sort of develops like so. so if you solved for the coefficients, which is kind of the point, right? If you want to know what a power series is, all you have to do is know what the coefficients are, and that'll tell you what it looks like, because we know it's x minus x naught to these powers. It's just the coefficients that are most important. So if you look at the coefficients that we get out, knowing that it's analytic, that means we can take each of these coefficients right here, and we can plug them back into our original power series right there, right? We've solved for them. Or in general, you could plug it in there for the nth one. And there you have it. Right? Now, what is that? Well, that's the Taylor series of f centered at x naught that we discussed in section 8.1. In other words, what this is saying is that if you have a function that's analytic at x naught, and you find the power series expansion for it at x naught, it's going to have to be the Taylor series, right? Because we proved it for the general case right here. So what this means is, if you ever find a power series that has some positive radius of convergence, like this one right there, that means that the power series has to be the Taylor series, if that makes sense.
Yeah.
Okay.
So yeah. So if we can express a function as a power series, then it is the Taylor series.
Yep, exactly. Yep. I think that's pretty much out. One more. And then finally, this is just some common expansion. So you'll notice that we did a problem earlier where we took a known expansion on some radius of convergence, and we used it to find some other expansions. These are like the useful ones that we use. So like, for example, this one right here, e to the x. This would be the power series expansion. This is the interval convergence. Usually you write it to the right, like so. Now, this would be useful. So one of the first questions that we ran across was, how would you integrate something like that? You can't do it using Calc 1 techniques. Well, what you could do is find an expansion for e to the x squared, which is this guy, where you replace x with x squared. So replace all of those x's with x squareds. The interval of convergence is still a negative infinity to infinity, and then you just integrate term by term. So that's how you would get around the fact that you can't find an elementary antiderivative. That's why we couldn't do those problems before. But with Calc 2 stuff, with power series, we can actually integrate. Now, our solution is going to be a power series solution. It won't look nice, but it's reasonable. It's got a pattern. It's got a closed form right there. So is that okay?
Oh, yeah. So like for integral of sine of x squared, you would just take that sine x Taylor series and then just put in x squared for each x. Okay. And then integrate.
And then integrate. So essentially it turns it into a polynomial, and then you integrate term by term. The radius of convergence isn't going to change. So it's still going to be this. It makes it really helpful. The other reason that we use power series is not only to integrate these, these functions that are non-elementary, or to find integrals that are non-elementary, but it's also for approximations. So, if you wanted to approximate e to the x using a power series, up to so many terms, like let's say the first 4 terms, depending on whatever level of tolerance that you wanted, you could just use the first 4 terms or so. And it's a polynomial. Technically, you don't need like some fancy CAS system to evaluate it. You could actually put these into a basic calculator and figure out what the approximation is. Of course, there'll be error because there's always some left over, but they converge to 0 pretty quickly.
Okay, cool.
Okay. All right. So I'm still writing up some notes for 8.3. I'm kind of changing it up a little bit, and I guess we'll discuss that on Monday next week, but let me stop.